Hello, hi, good evening. Good evening, everyone. How are you all? Good evening. Am I audible to everyone? Can all of you hear me? So, guys, welcome. Welcome to GATE Wallah and welcome to this session, which is PYQs on GATE Aerospace and propulsion topic. So, guys, before we start, I hope you guys are attending the classes of aerospace engineering, which the faculties are taking. So I think yesterday Shivam sir had taken your session. Hi, good evening. I'm good, guys. I'm good. How are you all? So, guys, today I'm going to take your session on PYQs for propulsion section. And guys, before we start, let me give you a brief introduction about myself. My name is Vinod Kumar Datusliya. I have done my MTech from aerospace engineering in from ISC Bangalore. I was All India rank 1 in GATE, and after doing my MTech, during the MTech time, I had appeared for ISRO as well. I was selected in ISRO also. I was All India rank 3 for ISRO, but I could not join ISRO because my MTech was not complete at that time. So I joined GE Aerospace, where I had designed aircraft engines. So the engines that you see maybe in Airbus A320 or Boeing, then you will see that there will be a lot of GE engines. You might have heard about an engine which is called as Leap 1, A, B, C. Leap 1, A is for Airbus, B is for Boeing, C is for Comac. Then I have also designed GE 9X, which is one of the largest engine in the world, which is going to be there in the service for next maybe around 20 years. So with that extensive background or extensive work ex, I am going to teach you all the propulsion part in aerospace engineering. So I'm sure you guys must have watched the 4 lectures which I had put up regarding the thrust calculations and the propulsion thrust, propulsive efficiency, then on the nozzles, you might have seen those. So guys, today we are going to do few questions on the which are the PYQs for this section, and probably from that you will get an idea on what are the different types of question that aerospace engineering has and which are asked in GATE. So GATE, we have a good quality of questions from aerospace. So guys, we are going to start it with one by one, and while solving these questions, what I will do is I will give you a time for around 1.5 minute, or for the larger questions you can take around 2 minutes to solve the question, and then give me your answers, and after that I will solve it. So the first question is regarding which one of the following engines should be used by a subsonic passenger transport airplane. So passenger aircraft which you see, a subsonic transport airplane for minimum specific fuel consumption. Specific fuel consumption is defined as the fuel consumed per unit of the thrust produced. Okay. So regarding the minimum specific fuel consumption, which of the engine should we use? I hope you guys might have seen the graph of different propulsive efficiencies with respect to the Mach number for different types of aircraft. You might have seen there is a turbo propeller aircraft, then you have turbo fans, then you have turbo jets, then you have ramjet, scramjet. So these are the ones. Okay. So I have the first answer. So Aryan has given the answer as turbofan engine. Very good. So guys, if you remember with respect to the Mach number, if you might have studied in your college days with respect to the Mach number, if we talk about the propulsive efficiency with respect to the Mach number, there are different aircraft. So the first aircraft that we used to have is turbopropeller aircrafts, which have the maximum propulsive efficiency range, which is very close to Mach number of 0.3 to 0.4. Then in this category comes turbofan engines, which have a much higher propulsive, which have a much higher Mach number, where the propulsive efficiencies are very high. So Mach number are in the range of 0.8 to 0.9. Then if we go still further, you see you have turbojet engines, and then apart from turbojet, you have rockets, ramjet. So those are coming in the last. So this is the turbojet where the Mach number is much, much higher. So in case of, he's asking about the transport airplanes which are using subsonic passenger transport airplanes. They generally run at Mach numbers of somewhere around 0.8 to 0.9. So in that range, the best engine is the turbofan engine. And if you might have come across the propulsive efficiency, we know that the propulsive efficiency is defined as 2 times velocity of aircraft divided by velocity of jet plus velocity of aircrafts. So in case of turbofan engines, we take, fan is actually designed to take a much larger mass of the air and then accelerate it by a small velocity. So you see, in case of turbofans, Vj is slightly or almost equal to Va. So we see that the velocities are accelerated slightly higher. Okay, so in that case, what you get is efficiency ranges are very high, maybe in the range of 80 to 90%. That is how you try to design. That is the reason why we have very large fans, which is where G9X engine has come. Okay. Next question. So next question says, on which one of the following thermodynamic cycle does an ideal ramjet operate? So ramjet engine, I hope most of you might have studied. On which of the following thermodynamic cycles? So ramjet engines are those engines which have, basically, if you might have seen, they are the engines where mostly you have they run at supersonic speeds. So the engine is sort of like this. There is only a duct that you see, which a ramjet engine has. Most of the ramjets has something like this. So they have only a duct, okay, where the air enters, and most of the time it is a shock wave which is present. Okay, so you see, the cycle that is employed over here is mostly the Brayton cycle. It is the Brayton cycle. So if you see the Brayton cycle, if you draw the Brayton cycle on a TS diagram, this cycle consists, or this cycle is the cycle which is used for aircraft, turbojets, turbines. So the engines which are there, it consists of 4 processes. You have a compression process where the pressure is increased. Then you have a heat addition process, which is a constant pressure process. So there you have the heat addition, and then you have expansion. Expansion can be there in turbine. So for turbofan, turboprop engines, the expansion is in turbine. For turbojets engine, it is basically the expansion of jet in the form of nozzle. In case of ramjet also, it is in case of nozzle. So that is how the actual cycle moves. So this is basically the Brayton cycle which is used by ramjet. So first 1 to 2 is where the compression happens. Then you have over here fuel nozzles where the fuel is imparted and where the combustion happens. And once the combustion happens, gases are expended through a nozzle. Okay, so you'll be going from location 3 to 4 in the nozzle, 2 to 3 over here in the combustor, and 1 to 2 probably the shock wave. Okay, so all of you got it correct. Very good, guys. Okay, let's go to the third question. So it says a turbojet engine is operating with afterburner off. So in case of a turbojet engine, so there is a nozzle, okay, and over here you see this is the full engine which is over here, and then you have finally afterburner over here, and it is operating in off condition. That means there is a normal engine in which nothing is happening. Okay, sorry, it will be over here. there is a normal engine where there will be a fan compressor over here, then there will be a combustor over here, and then there will be a turbine over here. Turbine would be running your fan, okay? A turbine would be running your compressor, and then there will be expansion happening. So in this condition, the afterburner is off. Now what happens is you switch on the afterburner. So what will happen? Both thrust and specific fuel consumption decreases, thrust increases and SFC decreases, thrust decreases and SFC increases, both thrust and SFC increases, specific fuel consumption. So what will happen in these cases? Which one is the right answer? If you switch on the afterburner, when we switch on the afterburner, what happens is we inject a lot of fuel. We inject fuel over here, okay? When you inject the fuel, at that time, what you are doing is you are providing more energy. You are increasing the pressure over here. When you are increasing the pressure over here, you are basically, what you are doing is when the gas is expanding, you are imparting more energy to the gas so that the velocity of the gases which is coming out from here could be higher. Okay, so when the velocity of gases coming out from here will be higher, so velocity increases. So when velocity increases, we have seen that the thrust is actually defined by mass flow rate of air multiplied by V exit minus V entry, V inlet. Okay, so there will be a velocity of air at the inlet, and there will be a velocity of air at air or combustion products at exit. So as we increase the velocity, what will happen? You will see that the thrust increases. Okay, so thrust and SFC decreases, thrust increases, thrust decreases. So A and C both are wrong. So B and D, thrust increases. What happens to SFC? SFC is the specific fuel consumption. Okay, generally guys, if you see in the afterburner, we dump lot of fuel. So when you dump lot of fuel, V increases. When V increases, the propulsive efficiency decreases. So when the propulsive efficiency is decreasing, basically the specific fuel consumption, which is the utilization of energy in form of thrust energy and the kinetic energy which you are providing over here. So you see that the SFC will also increase. You have to supply more fuel per unit thrust produced. Okay, so the right answer would be both SFC and thrust increases. I'm sure everybody might have got it. Okay. Yes, very good, very good. Now let's go to some numerical answer type question. These questions are mostly related to the compressors. So when I had taken those 4 lectures, I had asked you which all topics you want me to cover. A lot of you people have said, sir, let's take some topics on compressor. So I have got few questions on compressors. We can discuss as we are going along, we can discuss the theory of compressors as well. Okay. Anyways, we are going to teach you in compressors in a detailed manner. We will derive the Euler's equation for turbo machine, and then we will see all the compressors, probably centrifugal compressor, axial compressor, and though reciprocating are not there nowadays, but in outside application, reciprocating compressors are also there. So a centrifugal compressor requires 18 kilowatt of power to compress 10 kg per second of air. Consider the whirl velocity component is equal to the impeller speed, that is no slip. This condition is at exit. Okay, so at exit, okay, and no losses in the impeller. If the impeller has to rotate at 1900 radians per second, the diameter of impeller is to be. So you have to calculate what is the diameter. So quickly try to solve this question and find, or let's see whether you are able to find the diameter. Though this is very easy question, guys. I hope you guys might have come across the Euler's equation of turbo machine. And Euler's equation of turbo machine has 2 components. So let's say devices which have devices which are power consuming devices. So like compressor. So compressor power is generally defined as m dot into VW2 U2 minus VW1 U1. This is the Euler's equation. So generally for centrifugal compressors, what we have is, for centrifugal compressors, I hope you guys might have come across centrifugal compressors. The impellers are designed, they are designed in such a way that the whirl component at inlet VW1 is generally kept as 0. That means flow is entering actually and it turns radially. So it enters radially. When it is entering radially, there is no whirl component. Okay, so now you have very, it has been simplified. Power is equal to m dot into VW2 into U2. And it is already given that the whirl velocity component is equal to the impeller speed. That means this is radial blades of compressor. There are 3 types of blades at exit: backward curved, radial blades, and forward curved. Very good, excellent guys. Are Michael Stark, you are still here? Huh? Stark, you are solving questions for, you are from mechanical engineering and you are solving questions for compressor. I'm sure you must be finding these questions to be very easy, because we have studied in detail about the compressors. Okay, so guys, it is already there that P equal to m dot VW2 into U2. So now power is given, that is 1800 kilowatts. So 1800 into 10 raised to power 3 is equal to m dot is 10 multiplied by, now VW2 and U2 both are equal. So velocity of whirl at exit is U2. There is no slip. Okay, so you can write U2 square. So from here you can get U2 square is equal to 1800 into 10 raised to power 2. So 18 into 10 raised to power 4. And from here you can get U will be equal to somewhere around 446, I suppose. I'm not sure, because under root 18 is 4.5, 4.4 or 4.3. Okay, so under root of 18 is 424. So you have 424 meter per second. So U2 is 424 meter per second. And U2, you know that U2 will be equal to R2 into omega. And omega is already given as 1900. So from here you can calculate R2 will be equal to U2 divided by omega. That is 424 divided by 1900. Okay. So this will be divided by 1900. So 0.2232. So 0.2232. And from here you can get diameter D2, that will be equal to 0.446 meter. It's a very straightforward question. Very easy question. You are all-rounder, eh? Very good. I expect you to be getting good marks in GATE. Instead of being an all-rounder, you should get good rank in GATE. Okay. Next. This question is very easy. So an axial compressor that generates a stagnation pressure ratio of 4.0. So there is an axial flow compressor which has a stagnation pressure ratio of 4. That means the pressure, stagnation pressure at exit divided by stagnation pressure at inlet is 4. Operate with inlet and exit stagnation temperatures of 300 K and 480 K. If the ratio of specific heat is 1.4, then the isentropic efficiency of the compressor is. Very easy question. Very easy question. Try to find what is the answer for this. So what is the answer? Array, it should not take much of time. What is the answer? What is the answer? 0.80. Okay. So see what is given, that the stagnation pressure ratio is 4. So it is given as P02 divided by P01. This is given as 4. So if the stagnation pressure ratio is given, you can calculate stagnation temperature ratio T02 divided by T01 is equal to P02 divided by P01 की power gamma minus 1 over gamma, which is 4 की power 0.4 divided by 1.4. I think this will come out to be 1489. Okay. So from here, oh sorry, this will be T02S isentropic, because see, when the compressor is running, okay, when we draw the TS diagram for an isentropic process is 1 to 2S. But in actual condition, your compressor would be running with an isentropic efficiency. So the process of compression is not ideal. So that is not isentropic. So if the process is not isentropic, then it will not be landing at 2S, it will be landing at 2. So from here we define the isentropic efficiency of compressor, which is equal to T02S minus T01 divided by T02 minus T01. This is how we define the isentropic efficiency of compressor. So it is given to you that T02S by T01 is 1.489. So from here you can calculate T02S will be equal to 300. T01 is given as 300 multiplied by 1.4895. So I think this was coming out to be 445 Kelvin. Okay. So once T02S is calculated, now we can calculate isentropic efficiency of compressor is 445 minus 300 divided by 480 minus 300. I think this should come out to be 0.81. That is what it is coming, 145 divided by 180. Okay. Okay, so that was an easy question, not very difficult. Though in case of compressors, most of the time we define efficiencies in terms of total temperatures. But if the velocities are less, if the velocity changes are not very much, then these ratios can be written in terms of static temperature as well. Okay. Let's go to the next question. This question is very, very easy. So I think this was 1 marks question. Yes, GATE 2019. Very, very easy question. It says 1 kg of a diatomic gas is heated and its temperature increases from 100 Kelvin to 600 Kelvin. The energy added at constant pressure during this process is 500 kilojoule. Okay. The specific heat at constant volume for the gas is. So he's asking you what is the specific heat at constant volume, CV. Okay. So there is a gas in which you are adding certain energy and its temperature is increasing. So what will be the specific heat? Either you can calculate it, or if you might be knowing. See, he's talking about diatomic gases. And diatomic gases have certain specific heats. Okay. So it is given that at the heat added at constant pressure, 1 kg of diatomic, the energy added at constant pressure. So constant pressure QP is, it is Cp into delta T. Okay. So the energy added is 500, which is equal to Cp multiplied by delta T is 600 minus 100. So from here you can calculate that Cp is equal to 1.00 kilojoule per kg Kelvin. Okay. So this is what is Cp. So if Cp is there, now you know that for diatomic gases gamma is 1.4. Okay. So from here you can calculate Cv, that is Cp divided by gamma. Okay. And this will be 1.0 divided by 1.4. This will come out to be 0.714 kilojoule per kg. Okay, so you know that which gas is this? This is air. Okay, air has a Cp of 1.005 and Cv of 0.718. Okay. Chalo, let's go to the next question. Again, this question is also very easy, but it is a very typical question. So, though this question is easy, straightforward, but you will find it that the options are quite confusing. Okay. So, what is the answer? See, there is a small catch in this. Very small catch. If you are able to get that, probably this question is nothing. So the question is very big question, but it's a very small. It says it as in a single spool aviation turbojet engine. In a single spool turbojet engine. So what do you mean by spool? Spool is actually the shaft on which compressor and turbines are mounted. So you know that the work of turbine and work of compressor. Compressor absorbs roughly 40 to 50% of the work which is done by the turbine. So what we actually do is we put a compressor or different stages of compressor on the turbine shaft itself. So you have a turbine which has two stages, and you have a compressor which has 6 stages. So there will be 6 stages, 3, 4, 5 and 6. All will be mounted on one shaft. Okay, so this is how the combustor actually looks like. Okay, so this is how your engine looks. So it says which of the following is correct relationship between the total work output WT of a two-stage axial turbine. So work of turbine is WT and the total work required WC by 6 stages compressor. So there are 6 stages of compressor, so this is requiring WC. Now you see that this is a turbojet engine. In case of turbojet engines, the air which is taken is compressed by the compressor, then you add fuel to the air where the combustion happens, pressure increases, turbine is run, and the exhaust gases which are there, they are sent to a turbojet jet, which is the nozzle and from where the thrust is generated. So here the main purpose of a turbine is to run the compressor. So the work of turbine would be equal to work of compressor. The thrust developed by engine would be by the exhaust. Okay, so in this case, the right answer is work of turbine will be equal to work of compressor. I hope it is clear to everyone. Yes, it is clear. It's a very easy question. Okay, chalo. Now let's go to the next question. Again, this is a very good question regarding the staging. It says for a stage of 50% reaction, ideal axial flow compressor. So you have a compressor. Compressor has different degrees of freedom, reaction. So it says 50% reaction. So for a 50% reaction stage, what will be, which statement is correct? So the stagnation enthalpy rise across the rotor is 50% of the rise across the stage. Static enthalpy rise is 50% as rise across the stage. Axial velocity component of the flow at the rotor exit is 50% of that of the rotor entry. The static pressure rise across the rotor is 50% of the rise across the stator. Which one is the right answer? This is a very straightforward definition. So we know that for a degree of reaction, we generally define the static enthalpy rise divided by the total enthalpy rise. So the right answer is 50% reaction is the static enthalpy rise across the rotor is 50% of the rise across the stage. I am sure Everybody must have studied it. Okay. And for a 50% reaction, we see that this is a very special case. In case of 50% reaction where the degree of reaction is 0.5, you see that the angles of rotor and stator blades, if you might have if you might have studied the velocity triangles, so the compressor blades and the rotor blades, they becomes almost identical. So let's say if I draw it over here, so both the blades will be having the same shape. That means if you take this blade and flap it over here, you will see that the profile will match. So both the inlet angles will be same, and both the exit angles will be same. Okay, this is what is special case of 50% reaction. We will study this in detail, how this relation comes and what are the different angles. We will draw the velocity triangle. Okay. Next says an aircraft is cruising with a forward speed VA. So this question is related to the propulsive efficiency. Aircraft is cruising with a forward speed VA and the jet exhaust speed relative to the engine is VJ. What is the propulsive efficiency if VA by VJ is 2? Sorry, VJ by VA is 2. Sir, static pressure also rise across the rotor is 50% of. Was there a static pressure? I think there was something 50% of rise across the. It is not 50%. It will not be 50%. See, you cannot directly write it. Okay, let me give you a brief. So when we say the static enthalpy rise 50%, so let's say 10 joule of enthalpy and 10 joule of enthalpy is rising in both the stages. One is stator and other is rotor. Okay. So generally what happens is, if you see the temperature difference corresponding to this and corresponding to this will be same. Delta T will be same. So let's say I take a simple number. I don't go into the much specific detail. Let's say the temperature over here is 300. The temperature over here is 310 and temperature over here is 320. Okay. Now, can you tell me, let's say if the pressure is 1 bar over here. Okay. What will be the pressure over here and what will be the pressure over here? You see this process, which is the isentropic, the pressure rise which is over here, P2 by P1 will be equal to T2 by T1 ki power gamma over gamma minus 1, and P3 by P2 will be equal to T3 by T2 ki power gamma over gamma minus 1. If you will see this ratio will not be equal to this. Both the ratios will not be equal. Though the numbers would come not exactly, it will come nearly same. If you see, the pressure rise will come nearly same, but will not be exact. Okay. The difference of temperature is exact, because this is what is the enthalpy. The difference of temperature will be exactly 50%. Understood? Okay. If you try to do this, you solve this and probably you will get the answer. Okay. Chalo. Next. What is the propulsive efficiency? An aircraft is cruising with a forward speed VA and the jet exhaust speed relative to the engine at exit is VJ. So we have seen the propulsive efficiency. Propulsive is defined as 2 times VA divided by Vjet plus VA. Okay. So if we divide it by VA, we can write propulsive efficiency will be 2 VA divided by VA, and this can be written as VJ divided by VA plus VA divided by VA. Okay. So this will be equal to 2 multiplied by Vj by Va is given as 2. So 2 into 2 divided by 2 plus 1. So that is 4 sorry. I think I have, okay, this is 2 into 1. 2 into 1. So this becomes 2 by 3. Understood? So the propulsive efficiency is 0.67. Okay? Chalo. Let's go to the next question. Oh, this question is very good. This is related to combustion. Okay? So I want you all to study this and then try to solve it. At least try to get the stoichiometric equation. So a surrogate liquid hydrocarbon approximated as C10H12. So there is a fuel which is C10H12 is being burnt in a land-based gas turbine combustor with dry air. So dry air has 79% nitrogen and 21% by volume. How many moles of dry air are required for the stoichiometric combustion of the surrogate fuel with dry air at atmospheric temperature and pressure? So he is asking how many moles of air would be required to burn this fuel. Try to solve this question. C13. Okay, very good. You have solved it very fast. So let's see this. So you have, what is the fuel? C10H12. So you have C10H12. This is burnt in. So you have air. And you see the air consists of 0.21 times oxygen plus 0.79 moles of nitrogen. So 1 mole of air, 1 mole of air consists of 0.21 moles of oxygen and I hope he is asking turbine with dry air by volume, how many moles of dry air? Yes. So he is asking how many moles of dry air. Okay. So this is 1 mole of air which is 0.21 and 0.79. This will combine to produce CO2 plus H2O plus nitrogen. Okay. So there are, first we will do the balancing. So there are 10 moles of carbon. So while doing the combustion, there will be 10 moles of CO2. So we have balanced the carbon. There are 12 atoms of hydrogen. And you see, there are 2 atoms of hydrogen. So we will see that when 12 atoms of hydrogen, when they react, they will form 6 moles of H2O, which will have 12 moles of hydrogen. Okay. So now we will be balancing the oxygen first. So you have 10 into 2, 20, 20 plus 6, 26. So you have 26 atoms of, oxygen, which makes 13 moles of oxygen. So you require 13 moles of oxygen. But what you have is 0.21 moles of oxygen. So 1 mole of air has 0.21 moles. So to make this as 13, what we have to do? We have to multiply it by 13 divided by 0.21 moles of oxygen. 13 divided by 0.21 moles of dry air. So this is what we have to multiply. Now this equation will be balanced and the nitrogen that you will have will be 13 divided by 0.21 multiplied by 0.79. So this is the balanced equation. So now how many moles of air are required? So this is 1 mole of air, dry air. So the moles of air will be equal to moles of air will be 13 divided by 0.21. I think this will be somewhere around 65. So the right answer 61.9. Okay. This 61.9. Is it 61.9 coming? Is it exactly? Just let me check. So you have 13 divided by 0.21. Yes, this is 61.9. Okay, so the right answer is not 13. See, this is what you have to understand. Had he written how many moles of oxygen are required, if he had written how many moles of oxygen are required, then the answer would be 13. Aryan, your answer would be correct. But he is asking how many moles of dry air are required. So dry air, 1 mole of dry air has only 0.21 moles of oxygen. I hope you understand what is the mistake you are making. This was a very easy question, but it has become very difficult. Okay. Chalo. So let's go for one more question. Now the questions are slightly difficult questions. Okay. So you have these questions might take time. So in an air breathing gas turbine engine, so there is an engine which takes in air and then fuel is burnt. The combustor inlet temperature is 600 K. The heating value of the fuel is 43.4 into 10 raised to power 6. Assuming Cp to be 1100 joule per kg for air and burnt gases and the fuel air ratio to be much lesser than 1. Neglect kinetic energy at the inlet and exit of the combustor and assume 100% burner efficiency. What is the fuel air ratio required to achieve 1300 K temperature at the combustor exit? This is 1 mark question. Slightly lengthy question, but the answer would be very straightforward. Answer can be, you can get the answer in 1 minute or one equation probably. What is the answer you are getting? What is the answer? Guys, it should not take so much of time. It's a very straightforward question actually. Very good. So we can use the equation in combustor. Yes, steady flow energy equation in combustor can be used. So we know that this is a combustor. So in combustor, you have let's say air entering at location 1 and combustion products are getting at location 2. Okay? Let's say mass of air that is entering is m dot A. Cp of air is Cp air and temperature of air is TA. And here the mass of gases going out is mass of air plus mass of fuel. Then you have Cp gas probably, and then you have T gas, and you have fuel added mass flow rate of fuel, which has calorific value Cv and combustion efficiency Nc. So he's saying, so if first we will write the generalized equation, then we will write the approximate equation. So in generalized equation, we know that the enthalpy which is coming over here is m dot A Cp air into T air plus the energy which is getting added over here m dot Nc m dot F into calorific value. That will be equal to mass flow rate of air plus mass flow rate of fuel multiplied by Cp gas into T gas. Okay. So now this is the exact equation that we have, but he is saying mass flow rate of fuel is much smaller than he is saying the fuel air ratio, which is mass flow rate of fuel divided by mass flow rate of air, is much less than 1. That means mass flow rate of fuel is much less than mass flow rate of air. So what we can do is over here we can neglect m dot F with respect to m dot A. So you will have mass flow rate of air into Cp air into T air plus mass flow rate of fuel into efficiency of combustion is given as 1 multiplied by calorific value is mass flow rate of air Cp gas into T gas. Now he has not given you the difference between Cp gas and Cp air. He has given you both to be same. So if this is same, then you can take it on to that side. So you have mass flow rate of fuel multiplied by calorific value will be equal to mass flow rate of air into Cp. Then you have T gas minus T air. Okay, and from here you can calculate mass flow rate of fuel divided by mass flow rate of air. That will be equal to Cp into T gas minus T air divided by calorific value. Okay, so this will be equal to 1100 multiplied by the temperatures are given is 1300 minus 600 and Cv is 43.4. 43.4 into 10 raised to power 6. 43.4 into 10 raised to power 6. So if you solve this, you will get probably mass flow rate of fuel divided by mass flow rate of air as 0.00177, which is the first option. Okay, so the first 0.01. 00 or 01? 0.01. Is it 01 or 001? I think I was getting 001. 434. Okay, 01. 0.0177 you will be getting. Okay. So this was a pretty straightforward question, though you might have seen this equation in some other form also. You might have seen directly Cp multiplied by T exit minus T entry divided by calorific value. That is why what is the approximate equation actually. Okay, chalo. Now let's go to question again asked in 2024. An aircraft with a turbojet engine is flying with 250 meter per second speed at an altitude where the density of air is this. So again, this question is very easy, but the question is very lengthy actually. So density is given, the inlet area of engine is also given, the average velocity of exhaust gases at the exit of the nozzle with respect to aircraft, which is V exit or Vj, that you call 550 meter per second. Assume the engine exit pressure is equal to ambient pressure. So he has given you exit pressure and inlet pressure, both are same. This he has given you to probably remove the thrust which comes due to the pressure difference. And the fuel air ratio is negligible. The uninstalled thrust produced by the engine at these conditions is, he is asking you what is the thrust produced. So this is a very easy question actually. So we have seen thrust equation. Mass flow rate of air multiplied by V exit minus V entry. I hope you all remember that. So what is the thrust that you are getting? Very good, Arya. Very good gaming. So what is the thrust? So we know that the thrust is thrust will be equal to mass flow rate of air multiplied by velocity exit minus velocity at entry or inlet. Okay, which is nothing but the change in momentum of the air which is coming in. And mass flow rate of air that will be entering will be density multiplied by area multiplied by velocity in. So V exit minus velocity in. Okay. So he has already given you what is the density. So thrust will be equal to 1 multiplied by area is 1 into V entry is 250 multiplied by 550 minus 250. So 300 multiplied by 250, that will be 75,000. So the thrust will be 75,000 Newton. Yes, very good, Arya. Straightforward, nothing much to think about. This question is good, though this is not very difficult question as well, but this is a good question, 2 marks question asked in 2024. A multi-stage axial compressor with overall isentropic efficiency of 83% is used to compress air at a stagnation temperature of 300 K through a pressure ratio of 10. Each stage of compressor is similar and the stagnation temperature rise across each stage is 20 K. See, this is what I was talking about. Generally, the compressor stages, when you see, they have the same temperature rise. And if corresponding to this, if you see the pressure rise, no, the pressure rise keeps on decreasing actually. The pressure ratio that you see keeps on decreasing as you are going in the stages. So at initial stages, let's say the pressure is, the pressure ratio will be much higher, let's say 1.4, 1.3. But as you go along, the pressure ratio would diminish in the range of 1.05, 1.04. That is what happens in the last stages, where you have the compressor probably 13, 14 stages. There you will see that the pressure rise will be much slower. Okay. Okay. So calculate it. So there are 10, there is a pressure ratio of 10 and there are across each stage the temperature increase is 20 Kelvin. So you have to find what are the number of how many stages are there in the compressor. It's a very easy question though. Sixteen point eight, 17. Very good. Very good. So how do we solve this question? So guys, see what he has given you is, so the first concept is to calculate what is the temperature rise which has happened in all the stages. So it is given that at location 1, which is at the entry, the temperature is 300 Kelvin and there is a pressure rise. So pressure rise of 10 is there. So if the pressure rise of 10 is there, that means, and there is isentropic efficiency given for the compressor, that means the flow is not moving isentropic. There is some irreversibility. So you start from here, you want to reach over here, but you have reached over here at location 2. So first we will calculate what is the temperature T2s. Okay, and using the isentropic efficiency, we will calculate T2. So from the relation T2s by T1, that can be written as R to the power gamma minus 1 over gamma, where R is the pressure ratio, 10 to the power 0.4 divided by 1.4. So from here you can calculate T2s, that will be 300 multiplied by 10 to the power 0.4 divided by 1.4. How much it will be? So once you solve this, I think this will come out to be 579 Kelvin. Okay, and when you have got T2s 579, now you can use isentropic efficiency of compressor, which is T2s minus T1 divided by T2 minus T1. Now these all temperatures which I am talking about are the stagnation temperatures. So don't think that these are the static temperatures, because we have to talk everything in terms of stagnation. So I'm talking about the stagnation temperatures. So from here you can calculate T2 minus T1, that will be equal to 579 minus 300 divided by 0.83. So from here you can calculate T2 minus T1. How much is coming? It will come out 336.4. 336.4 Kelvin. So the temperature rise across all the stages is 336. So the number of stages will be equal to total temperature 336.4 divided by, across each stage there is a temperature rise of 20 Kelvin. Okay, so this probably N would come out to be 16.81. How much it is coming out? 16.33.6. So 16.82. Okay, and since the stage number cannot be fractional, so it will be the next higher integer. So the total stages would be 17. Is it clear? So the right answer would be 17. In actual compressor, what happens is the temperature rise that you see is somewhere in the range of 40 Kelvin. The real life compressor which I am talking about. The largest number of stages that we have is limited to around 14. So maximum stages that we have is around 14, and maximum temperature rise that you can see is somewhere in the range of 40 to 42 degrees centigrade, or 40 to 42 Kelvin. Okay, so somewhere around 500 Kelvin temperature rise you can expect. Okay, these are the compressor I am talking about. CFM engine has this, then LEAP has this. They both has 14 stages of compressors, and the temperature range is somewhere. So the temperature that we take in is around 300 Kelvin, and the maximum temperature that we have is around 790 Kelvin. This is the mota moti ballpark figure I am talking about. Okay, chalo. So now let's go to the next question. So we have two more questions, and these are good questions. Okay, again asked in GATE 2024, 2 marks question. So question says an aircraft with a turbojet engine is flying at 250 meters per second. The uninstalled thrust is 60,000 Newton. The heating value of the fuel is 44,000 kilojoule per kg. The engine has a thermal efficiency of 35% while burning the fuel at a rate of 3 kg per second. Okay. Assume that the engine exit pressure is equal to the ambient pressure. So that means there is no thrust which is developed apart from the jet thrust. What is the propulsive efficiency of engine under these conditions? Sir, which topic should I majority focus on? The whole propulsion. See, in the propulsion, if you see, there are a lot of areas. There are many areas from where the questions are asked. Generally, the propulsive efficiency, thrust equation, these are the two central equations, or these are the two central topics which around which the actual propulsion revolves. So you can expect questions from propulsive efficiency and the thrust. Then next important topic is about the Brayton cycle. You can get the questions from that. Then afterwards, we see air compressor. So there are a lot of questions which have been asked from air compressors also. Then there are topics related to shock waves, compressible flow. Those also you can focus on. Though it is not that there are no questions are not asked from other topics also, but these are the important topics. Okay. So quickly try to find what is the propulsive efficiency. So propulsive efficiency is thrust power divided by, I think, kinetic power. Forty to 50. Sir, when I attempt PYQ test series, getting 60 to 70 marks, but sir, attempt full mock length, I am getting 40 to 50. See, PYQs, it is, you might have solved the question somewhere before. So, PYQs generally, you know that what are the different types of question you have. That is why you are getting good marks. But in case of the mock test, the questions are most of the time 30 to 40% of the questions are new. And that is the reason why you might not be getting probably good marks. So what is the answer? Okay. So let's solve this. So the question says the engine is flying, or the aircraft is flying at 250 meter per second, and the thrust is 60,000 Newton. So since it is given that the thrust is 60,000 Newton and velocity is 250 meter per second, so you can see, you can calculate what is the thrust power. Okay. So the thrust power will be power is force multiplied by velocity. Force is 60,000 Newton. So 60,000 multiplied by 250, that is the thrust power. Okay. Now he is saying that mass flow rate of fuel is, it is given as 3 kg per second, and the calorific value of the fuel is 44 into 10 raised to power 6. So calorific value CV is 44 into 10 raised to power 6 joules per kg. So from here you can calculate what is the heat supplied. Heat supplied will be equal to mass flow rate of fuel multiplied by calorific value. And it is given that the efficiency, thermal efficiency thermal is given as 0.35. 35% is given, I suppose. Yes. So what is the thermal efficiency? Thermal efficiency is basically how much is the kinetic power, kinetic energy basically, okay, which has been given to the air. So kinetic power divided by the thermal energy, or the energy supplied, which is Q dot S. So from here you can calculate kinetic power. So kinetic power will be equal to the energy which has been given to the jet in form of kinetic energy, change in kinetic energy, will be equal to 0.35 multiplied by 3 into 10 raised to power 3 into 44 into 10 raised to power 6 in terms of joules per second. Okay, so this is the power which has been given. So now we can calculate propulsive efficiency. Propulsive efficiency is the thrust power, which is 60,000 multiplied by 250 divided by the kinetic power, which is 0.35 multiplied by 3 into 44 into 10 raised to power 6. Very straightforward. So propulsive efficiency will get equal to, I think it was coming out 0.325. Okay, you have got it correct, Aryan. Understood? So again, very easy question. So guys, this type of question you can expect. Again, this is related to the propulsive efficiency only. Okay? Chalo. So now let's do one more question, or in fact the last question in today's series. Okay? So a centrifugal compressor is designed to operate with air. Yeah, this is an excellent question. So there is a centrifugal compressor which has been designed to work under the air, and the leading edge of the inducer, tip of the inducer, which is the tip of impeller, the blade angle is 45 degree and the relative Mach number is 1. So this is the choking condition. So relative Mach number is 1. That means shock wave is about to form at inlet. The stagnation temperature of incoming air is 300 Kelvin. Consider gamma as 1.4. Neglect pre-whirl and slip. Find the inducer tip speed. So you have to find what is the tip speed of the inducer. This is excellent question. When we will be studying the compressor, at that time we will discuss this. We will make the velocity triangle at inlet. So let's I will solve this question because this is slightly difficult, and generally students find it very difficult to solve it. So let me draw the blade first, and then so I am drawing the blade first so that you get an idea of how actually the compressor blades look like. So this if you see from the front of the compressor, the diagram of inlet would look something like this. Okay, and let's say I have a blade over here, and the blade is radial blade. Okay, so the exit is radial and inlet is like this. Okay, and or let me do one more thing. Let me put the inlet over here so that you get to understand. Okay, so it is shown that the blade at entry is, the angle of blade at entry is 45 degree. Okay, so the blade is something like this. Wait a second. When I draw this, the entry angle should be like this. Okay, so your blade would be, the shape of the blade would be like this. This is how the blade would actually look like. Okay, so at the entry, you see this is where the entry happens. So now it is saying that when the flow comes, the flow generally enters axially, and when it enters axially, it is turned towards radial direction. Okay, so what it is saying is at the entry, the absolute velocity will be in this direction. The tip velocity, tip of the inducer over here, will have a u in this direction. So this will be your u1. This will be your v1. And it is saying that the inlet angle is 45 degree. That means this angle is 45 degree. So if this angle is 45 degree, then we know that v1 and u1, which is this velocity u1. So u1, when we draw the velocity triangle, we draw the velocity triangle like this. So this will be your u1, then this is your v1, Absolute velocity, this is your u1, and the relative velocity will be from u1 to vr1. So this is your relative velocity vr1. Okay, so the relative velocity is this. This is your relative velocity. Understanding? Okay, so this is how the velocity triangle at inlet would look like. Now what it is saying is the stagnation temperature at inlet T01 is 300 Kelvin. Okay, and it is saying that the relative Mach number, that means the velocity, relative velocity which is coming over here, has a Mach number of 1. Relative Mach number at entry is 1. So if the Mach number is given and if the total temperature is given, we can calculate what will be the static temperature, relative static temperature. So relative static temperature, you can calculate, you know that T01 divided by T1 will be equal to 1 plus gamma minus 1 by 2 into m1 square. So 1 plus 0.4 divided by 2 into 1 square, that is 1.2. So T01 divided by T1 is 1.2, and from here we can calculate T1 will be 300 divided by 1.2. So this is 250 Kelvin. So the static temperature that you get is 250 Kelvin. Now corresponding to this 250 Kelvin, we can calculate what is the speed of sound. Okay, so speed of sound will be equal to under root of gamma into r into T1. So we can calculate C with C1, in fact, at inlet it is equal to under root of 1.4 into 287 into T1 is 250. Okay, so how much it will be coming? So the value of this would be, just hold on a second, value of this will be square root of 1.4 into 287 into 250. Okay, so 316.9. So C1 will be equal to 316.9 meter per second. Okay, now this C1 is 316.9. So can we say the VR1, which is the relative velocity, will be equal to C1 also? Because the relative Mach number is 1. If the relative Mach number is 1, that means VR1 divided by C1 is 1. So this also becomes C. Okay, so VR1 will be C1, which will be equal to 316.9 meter per second. And from here, you can calculate what is the velocity U1. So this is your U1. So U1 and V1, and this is VR1. You know that if the angle is 45 degree, so U1 divided by VR1 will be equal to 1 by root 2. Sine of 45 degree or cos of 45 degree, whatever you want to write. So VU1 divided by VR1 will be equal to 1 divided by root 2. That is equal to 300. Sorry, U1 will be equal to 1 by 2, and from here you can calculate U1 will be equal to VR1 divided by root 2. That is 316.9 divided by root 2. That is 224. So U1 will be equal to 224 meter per second. So the inducer, the velocity of the tip, inducer tip speed. So the inducer tip speed will be 224 meter per second. This is I find this is one of the best questions. This type of question are really the questions which test your thorough knowledge about the subject. So this question, when it is testing the knowledge, it is testing two concepts. One is the compressible flow, where you are using T0 by T1 is equal to 1 plus gamma minus 1 by 2 m square. And second, the concept it is testing is the compressors. Okay, so how much of the compressor you know. Okay, so I hope with this, guys, you might have got a fair idea of what are the different types of questions that are asked in propulsion. I have tried to take a few questions. I just wanted to give you a glimpse of different types of questions which are generally asked. Okay, and I'm sure you guys might have enjoyed the lecture. You might have found that the quality of questions was good. Okay, And guys, this is just to give you a glimpse on what is the level of preparation or what is the level of subject that we will be teaching you all. Okay, so those of you who are serious aspirants, those of you you really want to prepare for GATE in aerospace, guys, you can join our batches where we will give you the detailed explanation about everything. Sir, I have a question. Yeah, tell me, Vampire. Vamp 6895. Tell me quickly. So in case, guys, any one of you have any other question, you can let me know. You can put it in the chat box as well. Or those of you who are going to watch it later on, guys, you can put your comments in the comment section. Probably we will try to reply to your queries as soon as we see those messages, and we will also try to take on the subjects if you want to take if you want us to take any topic that you want us to teach you. Okay, so you can let us know about that also. Is it clear? Chalo. So, sir, I am in my final year BTech mechanical. Should I give GATE ME or aerospace? You should give for ME, yaar. Why aerospace? Aerospace, you will not be able to solve the question. The level of questions that are asked in aerospace. See, you are telling it because you have not understood it. The level of questions which are asked in GATE is much, much tougher as compared to the mechanical. Final year, okay. First year, you are saying. Try to prepare for mechanical, not... and you are saying, I intend to specialize in aerospace. Don't specialize in aerospace. Specialize in mechanical. You will enter in aerospace very easily. But if you take a specialization in aerospace, you will not be able to enter in mechanical very easily. Flight mechanics के question कब होंगे? We will let you know. ठीक है? So सर की availability के basis पे probably we will let you know. ठीक है? So with this, let's stop it over here, guys. I hope you might have enjoyed it. Okay? So see you in next other videos or next lectures. Okay? Thank you.